of senior presentations. This is really the culmination of the degree program for these students in our 3 degree programs, industrial supervision, advanced manufacturing, and engineering. At the end of their final semester, they've completed a project that they've worked hard on for a number of months, and they're all here to present to you and give you the opportunity to see that they can do something besides walk across the stage at the end of the 4 years. And I think you'll be impressed with what you have to hear today. Our first presenter will be introduced by his faculty advisor, Mr. Dave Eller.
All right, thank you. I'd like to introduce Chase Meyer. He's a senior, ready to graduate in advanced manufacturing. He's going to talk about his senior project at Hunter Douglas. Chase.
Thank you, Mr. Eller. My name, again, is Chase Meyer. I completed a school capability study at my internship at Hunter Douglas in Owensboro, Kentucky. Hunter Douglas is a worldwide company that specializes in window blinds and architectural products. As you can see, these window blinds contain various different parts. The facility in Owensboro, Kentucky produces die-cast parts, injection molding parts, and assemblies that go inside these window blinds. Each one of these window blinds has a spool in each side of the window blind. That is the most produced part at Hunter Douglas. It is injected molded polycarbonate and requires very tight dimensional tolerances. Most critical is the spool diameter around the flange. It is a 0.778 inch diameter with a plus or minus 0.002 tolerance. This is very important because if those were not kept in with spec, there's one spool at the high end of the diameter and one at the low end. There would be called skew issues. The window blind would row up and down crookedly, which is unacceptable. There are 2 molds that can produce the common spool. And when both these molds used to run at the same time, there were skew issues occurred. Both molds would be within spec by the quality criteria set forth by the engineers at Hunter Douglas, but one would run at the high end and the other would run at the low end, causing skew issues when the spools would be mixed from mold to mold. This caused our customers to reject spools, and currently only one mold, M890, runs production parts. M890 runs on a 142-ton, 10.2-ounce shot Toshiba hydraulic injection molding machine. It can only run 7 of 8 cavities due to the one cavity running oversized, causing skew issues. This mold has over 4 million cycles when it was only expected to run for around 1 million cycles. A cycle, I'll show you here in a little bit as a video, is actually when the mold opens and closes and injects the parts and then closes back up again. That's a complete cycle. And because of these 4 million cycles, it has been down for 175 hours of tooling. Here's a picture of Crest 30, which mold M890 runs on. The mold's there in the center in the red. And then here's a short video of the actual cycle of the mold. The mold is opening. You can see the spools being ejected by ejector pins, and then on the left-hand side is a runner system, which actually allows the spools to form fully within inside the mold. The mold will close. Currently, right now, plastic is being ejected into the mold, and then the plastic is allowed to cool, and then the ejector pins will knock out the spools again. This mold can only run 7. It's a 3-plate mold. It is a cold runner mold as well. Mold M1060 runs on a 198-ton, 5.5-ounce Nessie hybrid injection molding machine. The hybrid machine is a little bit more efficient. It uses a combination of hydraulic and electric power. This one. This mold has a little over 1 million cycles and can run all 8 cavities. And we believe that it can also run faster cycle times due to just the process capability studies. Here's mold Crest 20 with the mold there in the center. And here's another short video of that process. Again, this is cycle. I'll also refer to this as the shot. The shot contains 8 cavities, 8 spools each time. You'll actually be able to identify each cavity by a cavity identifier inside the spool, and that's how I complete the testing. I'll talk a little bit more. Again, it's a 3-point mold with the runners on the right-hand side and then the spools on the left-hand side. Process capability study would be completed on mold 1060 to see which process would row up the standard deviation. We would vary the melt temperatures, the hold pressures, and the mold temperatures. We'd collect 10 shots of 8 cavities each and calculate the standard deviation from the average measurements. The process variables included melt temperatures, hold pressures, like I said before, and mold temperatures. The melt temperatures, the lowest melt temperature we could use was 570 degrees, and the highest would be 600 degrees. The lowest hold pressure we could use was 24,000 psi, and the highest is 29,000 psi. And the mold temperature is actually regulated by a thermolator, which is hot water running through the machine, and that was either set at 170 degrees or 190 degrees. The melt temperature is varied by heater bands along the screw, which would actually melt the material, and the hold pressure is actually the hydraulic or electric force holding the mold together. We found out these variables by testing. The low end is process A, and this is the lowest the mold could run without running a short shot or shorts. This is actually when material is not fully formed around that part. And then process F is the highest it could run without producing flash. Flash is extra material, which would also lead to an unacceptable part. The testing equipment used was a Zoombach laser measurement device with a custom fixture, so we could take 4 different measurements and we could average those measurements and receive an average spool size. Instead of just taking a measurement at one place, we would get measurements all around the spool. This is actually taken a little bit higher, so it's not exactly within the 0.778 tolerance. It's a little bit lower because there is a flange or taper along the spool, making it a little bit smaller diameter. Standard deviations vary from the very highest at A to the very lowest at F. As you can see, F is very similar to the chart or the bar graph on the furthest right, which is the production. Actually, it sampled 10 shots from the production mold as well, M890, and we thought process F is very similar to that, so we'd use that process F throughout the rest of the process. Process F is low standard deviation. It uses a combination of the highest melt temperature, the highest mold pressure, the highest hold pressure, and the highest mold temperature. This also led to lower cycle times, and we believe that process F was best fit because the plastic material was actually pushed into the mold the best and was actually able to fully form around each cavity to form the spool. Process F, here's the chart. As you can see, it's very close to the upper limit, but it has a very low standard deviation, what we were looking for. Next would be a production simulation trial to test and see if process F would be capable of running in a production setting without any variables, without any trends going up and down. Just we were looking for an even trend over the entire run. So for this, every 10th shot was collected for a total of 540 shots. So 54 shots were collected of 8 spools each, and then those would be tested on the Zoombach laser measurement device. As you can see, we were testing them and we found a steady increase over time. We were wondering, where did this come from? What happened? So the next day, we figured it could be due to temperatures. So the next day, we tested the same spools and we plotted the temperature over time. As you can see, as the temperature increased over time, so did the spool diameter. So that led us to believe that thermal expansion was the main cause of the spool diameter increase. I did this summer. The day would start out around 74 degrees and would increase to about 97. That would feel great today. The thermal expansion of the spool diameter, the calculated is a 3.65 times 10 to the negative 6 inch per Fahrenheit. And the standard is actually 37 times 10 to the negative 6 inch degree Fahrenheit. So it matched up very very consistently with the standard, and we truly believe that thermal expansion was the cause of increase. So then after that, we decided to test the spools in a controlled environment in the quality department. The spools then came out evenly. These are the same spools again, and as you can see, very consistent, which we were looking for, making us believe that process F would be capable in a production situation. Standard deviation for each cavity and overall, as you can see, these were very high, even for the 0.78 diameter, so that led us into plating the mold. Mold 1060 would be plated in order to close the upper limit to find into our desired range, which I'll talk about here in a little bit. Testing would be completed again. This time we would only take 25 samples from every other cycle, so a total of 50 cycles were ran, since we already found out that process F was capable of completing or running in a production setting. It costed $855 to plate mold 1060. After plating, we found out that we had overcorrected. The spools were really low, but we also found out the standard deviation is much lower, which we were looking for. So we met one of our goals by plating the mold. Comparison, as you can see, before plating, it's all towards the upper limit, what we weren't looking for, and then after, it's very low. We want to get into the red range right there, the desired area, to actually run these spools for a production tool. I completed an economic analysis. I compared the cost. As you can see, M1060 actually costs more to run on an hourly basis. This is because it runs, it uses more material because it actually has the 8th cap and the 8th spool instead of just 7 on M890. But the hourly revenue is actually double that, so it's more than beneficial to take over M1060. It would only take 32 hours to recover the $855. To recover the cost of mold and plating, it'd only take 3 days. So my time, I calculated that I use about 70 hours of my time at a $15 hour rate. So it'd only take 3 days to recover that cost. And then after that cost was recovered, they could possibly see a $3,200 in extra profit. My recommendations is to continually rework mold 1060 so it can run production parts. What they could do is use a combination of polishing and plating again to achieve this in the desired range. And actually currently I went beyond the scope of my project, and we are already in the desired range. We are just waiting to hear back from our customers and engineers to ensure that these spools are okay. We're going to send off some samples here, and they're going to test them in window blinds and assemblies, so to see if we can actually change over and use mold 1060. I would like to thank Hunter Douglas in Owensboro, my liaison Roger Goris. I would like to thank the University of Southern Indiana Engineering Department, all the professors that helped me throughout my entire college career. I'd like to thank my faculty advisor, Dave Eller, for his help, and I'd like to thank my family and friends for their continued support throughout my college career. Thank you. Are there any questions?
Let's see. Okay, we're working. Any questions for Chase on his presentation? Okay, so I guess I have to ask some questions. All right, because we can't let him out of here for free. I mean, that's just the rules of the game. You describe a process by which you plate and polish molds. For the audience's benefits, how much would it cost to just flat out replace the mold? Do you have an idea on that?
That was beyond the scope of my project, but currently they are running a prototype tool for a similar spool. It's a single cavity, and they're waiting to hear back from the results from that one. We ran production on that mold this past week, and then they'll send that off after they get approval for that spool or that prototype mold. Then they will send it off for a larger build for like an 8 or 16 cavity mold, so that that can be run in the future.
Okay, so they are looking into the
Mhm.
possibility. How much additional time, how many additional cycles do you think they would like to try to get out of these plated molds?
Honestly, they'll probably run those until that new mold comes in.
Okay.
Until the prototype mold comes in and comes back to be completed. There's no way they could keep up with the volume with just a single cavity mold, so they would have to have a multiple cavity mold, either an 8 or 16. So they're gonna investigate that. So the tools are actually built in China at our facility there, so it's gonna take probably months and months. I know they started building this prototype mold this summer, and we just received it at the beginning of this month. So it's going to be a little bit of time. I would say it'd probably be about the end of the summer before we would, end of summer 2014, before we'd actually receive the new tool for actual production run. And then they would probably do testing like this to find the low standard deviation and everything like that. I could foresee them using this stuff in the future as well.
Okay. And-
So this mold had diameters that were too big at first, and then the plating made it too small. Why did that happen?
Well, they really didn't know where to go. They just used it was a nickel plating, and they just used electrodes and they went inside of there. So they just went where they thought they should. I'm not really for sure, as beyond the scope of this project, where the engineers took the measurements in these spools. I believe they just used my measurements, and then they correlated that and then plated each mold accordingly. That's why you saw the lower standard deviation with the same process. It's just because they used my data and added accordingly to each cavity.
So does the plating had enough thickness? That's what made the cavity, or the diameter of the spool smaller.
Yep. Yep.
All right, other questions? All right, let's give him a hand.
Thank you. Thank you. Thank you. Thank you. Thank you. Came together. Yep.
Dr. Mitchell, do I go ahead and shut this off?
Yeah, go ahead and shut